Okay, so now time is 2 o'clock. So this is the session for week 7. So we will uh, revise all the topic one by one. So there are 4 topics basically in this week. First is balanced binary search tree, and second is greedy algorithm. And inside the greedy algorithm, there are 3 topics: interval scheduling, minimized readiness, and Wookman algorithm. So we will revise these topic one by one. If you have any query in these topics, so you can ask in between. So okay, first topic is balance search tree. My screen is visible to all?
Yes, sir.
Okay. So first is balance search tree. Basically, what is the meaning of balance search tree? So we have already seen the binary search tree in week 6. So what is the issue with normal binary search tree? So if, for example, if we create the binary search tree like a sequence 1, 2, 3, 4, 5. So if we create the binary search tree for the given sequence, so what are the type of our binary search tree will be? So we will insert the first node 1. Then after that, when we will insert the 2, so 2 will come at the right side of the 1. So 2, same for the 3. So we will compare every time from the root nodes. So 3 we will compare from the 1, so it is greater than. So we will compare again to the 2. So it is greater than the 2. So we will add at the right side of the 2. Okay. Same for the 4. So we will compare from the 1. So it will add at the right side of the 3. So same for the 5. So this is also a binary search tree, but we cannot use efficiently for our any operations like a searching or insertion deletion operation. So this is simply like a linked list type. Okay, simply is a linear linked list type. So if you want to perform any search operation on that, so it will take a n time, before n times, because all nodes are connected in a linear way sequentially. So this is so what will be the height of this binary search tree? So height, if we are considered that the root node of rootnet, if we are considering that the empty tree height is 0, so the total height of this tree is equal to 5. So this is not useful. So our basic purpose is not satisfied for this type of binary search tree. So we need to some any algorithms to balance this tree. So balance means, so our tree should like in this format, like this. So this is, we can say that this is the balanced binary tree. So here if we are considering the height of the left subtree and height of the right subtree, so it should be the similar. So here if we are considering the height of left subtree, so basically we consider that this node height is 1, this node height is 1, this node height is 2, the same for 2, 1, 1, and this height is 3. Okay, so height of the subtree, so left subtree height is 2 and the right subtree height is 2. So both are similar, so we can say that this is a balanced binary search tree. So basic purpose our the balanced search tree is we want to balance our tree. So this is the basic purpose, and after that there is one algorithm to perform this balance operation, so that is called the Avl tree. So what is the Avl actually means? So Adelson, Waleski, and Landis. So this is the name who developed this. So what is how it works? So what is the algorithm to perform the balance? Just wait. So in Avl tree, so we consider that if in our tree, if height left for left subtree height minus right subtree height. If left subtree height minus right subtree height is less than equal to 1, okay, less than equal to 1, that means our tree is the balance. So this is the formula to for the AVL tree, where we consider that if left subtree height minus right subtree height is less than equal to 1, so this is the absolute value. Okay, this is the absolute value. If it is less than equal to 1, then we consider that our binary tree is balanced. If the value is greater than 1, like a 2, so 2 3, so we consider that our tree is not balanced. So this formula is also called, sometimes we call this slope, and sometimes we also call the balance factor. Balance factor. Okay, so for example, if we create so generally we create the binary search tree in the same way, like a binary search tree. So for example, if we have a binary tree, for example 1 2 3, okay, so we calculate this slope or this balance factor every time when we insert the nodes in the binary search tree. So for example, if we are inserting a 1 in our tree, so 1, so what is the left subtree height is of this one node is 0. So right subtree height is 0. So that means 0 minus 0. The balance factor value is, or slope value is 0. So this is the balance tree. After that, in the next step, when we insert 2 in this tree, so 2 will insert at the right position. Okay. So we will once again we calculate the slope for every node. So what is the slope for 2? So left height is 0, right height is 0, so 0 minus 0, 0. Same for the 1, left height is 0, but right height is 1. 0 minus 1 minus 1. Okay, we can write as a absolute value also. So we are removing this. Okay, so we are consider that we are taking the absolute value of the difference. Yeah, so still this tree is also a balanced tree. After that, we are inserting a 3. So 1 2, then 3 will come after on the right side of the. So when we calculate the balance factor again, so 3 is left 0, right 0, 0 minus 0 0, and what is the balance factor of 2? So 0 minus 1 1, and what is the balance factor of 1? So 0 minus 2. What is the longest path? We can say, we consider that the height of the tree. So 0 minus 2 is 2. So now in this situation, we can say that this is not a balance. So for this type of situation, when the balance factor of any node become 2 or greater than, so we consider that our tree is not balanced, and then we apply some rotations to make a balanced tree. So what are the type of rotations now? So there are 2 types of rotation generally. First is left rotation, or we can say that left rotation, and second is right rotation. So left rotation, when we perform the left rotation, and what is the meaning of this left rotation? So for example, this type of situation, so we have already seen 1 2 and 3. Okay, so the balance factor is 0, balance factor is of 2 is 1, balance factor of 1 is 2. Okay, so now this is become a unbalanced tree, so we will perform the left rotation on that. So the balance factor value of 2 is at that node. Okay, that node 2. So we will check that what is the balance factor of child of this node. Okay, so what is the balance factor of child of this node? So who is the child of 1 2? So we have to find out that there are 2 types of rotations. Okay, so I'm just writing the exact value. This is -1, this is -2. Okay, So this type of situation. So if balance factor of our one node is the negative -2, so we will check the right side of the child of this node. And what is the balance factor of the right child of node? So it is also a negative value. So that means the last node added on the right side of the tree. Okay, so where balance, so weight is increased on the right side of the two node. So at this situation, we perform left rotation on node that have the balance factor -2. So left rotation is what? Basically, we rotate the tree on the anti-clock way. And this is the point. So we will rotate the tree. We will, so this one become a left child, and two will replace at the one position, and three will move up. Okay, so three this time. This is the rotation. So this is the point where we will rotate this tree on the anti-clockwise way. So this become like this. So the balance factor, now we will once again calculate the balance factor. So the balance factor of 1 is now 0 minus 0, 0, 0 minus 0 is 0 once again. What is the balance factor of 2 now? 1 minus 1, 0. So it become a balanced tree. And what are the second type of situation? This is the left rotation for one type. So there are actually four types of rotations some we have faced. So same the reverse way, right rotation. So right rotation is what? When, for example, we are inserting that 3, 2, 1. So 3 will become a root, 2 will come on the left of 3, same for the 1. So balance factor of this 1 is 0. This 2 is 1 minus 0, 1. The balance factor of this 3 is 2 minus 0. So 2 minus 0 is 2. So now we will apply the right rotation on that. So this is the right rotation. So we will apply the right rotation on node 3. So this is the similar to previous one. Basically, we are just reverse the rotation type. So 2 come at the 3 position. Now 3 become a right child of the 2, and 1 will become a left child of 2. So this is the simple straightforward rotation. So after that, after rotating, so balance factor become a less than 2 now. So 0, 0, and 0. There are some more situation come sometimes. So what are the situation? For example, if we have a sequence 1, 3, 2, we are inserting this type of sequence. So this is the root node 1. After that, 3 will add at the right side of 1, and 2 is the left side of the left side of the 3. Sorry. So balance factor of this 2 is 0 minus 0, 0. And what is the balance factor of 3 is? So the 1 minus 0, 1. And what is the balance factor of this 1 is now? So this is the situation. So left height is 0 and right height is 2. Okay, right height is not 2. So balance factor is -2. Okay. So in that case, so the different, this is the different type of the case. So we will check the so there is the -2 value. So we will check the right child. What is the balance factor of right child? So balance factor of right child is 1. So this is the positive value. So this is positive value. So then we will check. That means the weight is increased on the left side of the 3. So we will apply here two rotation on this case. So first rotation is the right rotation we will perform at the third node. So after right rotation, so this will become, so this is the right rotation on third node. So this become like 1, 2, and 3. Okay. After that, we will perform the left rotation on 1 in this case. So these 2 come at the parent node position 1, then 3. After that, we will if we can calculate the balance factor, so it become all balance factor value will reduce to less than 2. So now this is 0, this is 0, this is also 0. So this is the another case where we have to apply the 2 rotation. Similar for the reverse side. So if we are applying, for example, 3, 1, and 2. So this tree become like a 3 node at the parent position, 1 on the left, and 2 on the right of 1. Okay, so balance factor of this is 0, this is -1, and this is 2. Okay, so in that case, if your balance factor is 2, we will check the positive value, we will check the left side position. So if the left side position value is negative, so we will apply 2 rotation. First rotation on this node, the child node of the 3. This is the left rotation. So after this rotation, our tree look like 3, then 2, then 1. After that, we will apply the right rotation of 3. So this look like 2, 3, and 1. So balance factor is now become 0. So after rotation, the balance factor will reduce to 1 or 0. So these are the rotations. So we have to apply when we make a binary search tree. So these all type of condition come when we insert the node in binary search tree. So we are taking one example here. So for example, we are creating a Avl tree. So for example, we have a sequence 1, 3, 2, 8, 4, 5, 7. Okay, so we have a sequence, and the question is what will be the Avl tree for this sequence. So we will start one by one. So this is the first node. We will insert, the balance factor is 0. Okay, so now next step we will add the 3. So 1 and 3 will come at the right position. Balance factor of 3 is 0, and the balance factor of 1 is -1. Okay, now next, now it is the balance. Now we will insert the 2 node at the this tree. So 1, this become like 1, 3, and 2. Okay, so balance factor of this 0, this is 1, this is -2. Okay, so we will apply the 2 rotation on that. So first rotation is the on 3. So now it become a 1, 2, and 3. Now second rotation we will apply on the 1 node. So 2, 1, and 3. Now balance factor is all 0. Now next node 8 we will add at the final version of rotated tree. So we will add this tree. So now it become a 2, 1, and 3. 8 will come at on the right side. So 8 will come at this position. Now balance factor we will calculate again. So this is the 0, this is my -1, this is -1, this is 0. Okay, now we will consider that this is a balance. Now we will add the 4. So 4 will come 2, 1, and 3, then 8, then so 4 is greater than 3, less than 8. So 4 will come here. Okay, so balance factor of this 4 is 0. This is 1. This is -2. Yeah, this is -2. This is 1, 2, 3, and this is also -2, and this is 0. Okay, so balance factor is this. So when the balance factor of any balance factor become greater than of more than 1 node, so we will apply the rotation on the first node from the bottom side. Okay, so we will check the rotation for this 3 node. Okay, from the bottom first. So from bottom side, these three come first. So we will apply the rotation on that node. So what are the type of rotation? So this is the -2 value. So we will check the right side value. If right side is the balance factor of the child node, right side child node is the positive. So we will apply 2 rotation again. So first rotation on that right rotation. So it become like a 2, 3, and 4, and 8. And second rotation we will apply on this 3. So this is the what we say the left rotation. Yeah. So 2, this is 1. Now this here come 4, then 3, then this is the 8. Okay, now after that we will calculate the balance factor. So this is now 0, this is 0, this is 0, or no, this is 0. It also reduced. So upper value which have already increased, we have already reached this value already reached to 2. So this is also reduced after the rotations. So now this is, so the right height is maximum height is 2, and left height is 1. So 1 minus 2 is -1. So now tree become balanced. Now after that, next node is 5. So we are applying that 2, 1, 4. So this is 3. This is, so 5 is greater than 4 and less than 8. So 5 we will insert at this position. After that we will calculate the balance factor. So 0, 0. So leaf node is always 0. So what is the balance factor of 8 is 1. What is the balance factor of this 4 is, so 1 and 2, so -1. And what is the balance factor of this 2 is now 1, 2, 3, and 1. So this is -2. Okay. So now balance factor become increased. We have so balance factor reached at 2 value. So we will apply the rotation on this 2 value. No. So what are the type of rotation? So the value of the child node, balance factor value of the right child node is negative. So this is the similar way where we have already seen like 1, 2, 3. Okay, so we will apply the rotation only on this first node. So we will apply the rotation only on node 2. What are the rotation? Rotation is the left rotation. So we will apply the left rotation on 2 node. So this time, so this 4 will come at the top position. Now 2, now 1, this is, now this is the 8, and this is 5. So where this 3 value will come now? So for maintain the binary search property, if 4 node, if this 4 node become a parent node, so we will add this 3 value at the right side of the last parent node. Okay, this one. So after this type of rotation, so now this is also a binary search tree. So there is no violation of binary search tree. So this is the rotation. So now after the rotation, if we calculate the balance factor, so this is 0, this is 0, 0, this is 0. Now this is 1 and 2 and 2. This is 0. So now it become a balance. There is only last value 7. Yeah. So 7 we will add 4, 2, 1, 3. Okay. So 8. So 4 is 7 is greater than 4. Yeah, okay. So 7 is greater than 4, less than 8, and greater than 5. So 7 will come at this position. Okay, so balance factor now is so 0, 0, 0. So 0. Now this is -1, and this is 2. Okay, so 1, 2, 3, and 2. This is -1. Okay. So now this is the another situation. So we will apply the two rotation on this part. So first rotation we will apply on the 5. This is the left rotation. So 4, 2, 1, 3. So the first rotation is 8, then 7, then 5 after first rotation. So this is the type of rotation. Now we will apply the second rotation. This is the right rotation. So now 4, 2, 1, 3. This is 7, this is 5, this is 8. Okay, so balance factor is now 0, 0, 0, 0, 0, 0, and 0. So this is the final balance binary search tree. So for the given sequence. So this is the given sequence where we are inserting one by one, and this is the final version of balance tree. So this is the procedure to create a Avl tree, and it is a balance tree. So there's some properties also given. So after creating the binary search tree using this Avl method, we can perform the any searching operation in the log times, any insert or delete operation in log times. So we can basically improving the complexity in the worst case situation. So in binary search tree, the worst case situation is this operation taking the big O times, but it is reduced to log n, where we are creating the binary search tree using Avl method. So okay, so there are two important formula for Avl tree. So this is the formula for what is the minimum number of nodes in Avl tree. So this is the formula where we can calculate the minimum number of nodes in the Avl tree. SH equal to SH minus 2 plus SH minus 1 plus 1. So where S0 and S1 value is given. So S0, what is the S0 value is? So S0 means if height of balance Avl tree is 0, so there is no node. Okay, so the number of nodes is 0. If height of the Avl tree is 1, that means S1, so there is only one. So the first is, so this is the S0 empty tree, and this is the S1. So there is only one node. So after that, if we want to find out the next minimum node in the two heights, what is the minimum number of nodes with the two heights? So we can apply this formula. So S0 plus S1 plus 1. So what is the value is? Now 0 plus 1 plus 1, that means 2. So we can create this type of two-height tree. So this is for like that. There is one node and there is second. Okay. So we are inserting a one parent node of this after combining these two version of the tree. So this is empty, this is one node, so we will apply this. So this is also a balance tree, Avl tree. So because balance factor of this one 0 and this is 1. So this is now a balance. Same for the S3. If we want to calculate the S3, what is the minimum number of node of height 3? So similarly, S1 plus S2 plus 1. So what is the S1 value is 1, S2 value is 2 plus 1. So this is the node we will add into the parent, add as a parent node every time. This is the value of for that. So we are combining these S1 and this S2 tree. So this is like that, for example. And for example, we are considering that this is the left part and this is the right part. Okay, so this S1 is the right part. After that, we combining these by a one parent. This one. So this is also a balance tree which have height 3. So balance factor is now 0. This is 1. This is also 1. This is 0. It is also a balance tree. So we can calculate the minimum number of nodes of height any height using this formula. So this is one important formula. What is the minimum number of nodes in the AVL tree of height h? And second formula is similar to a normal binary tree. What is the maximum number of nodes for height h? So maximum number of nodes we can calculate simply like what are the type of our tree will be. Similarly, this type complete binary tree. Okay, so here height is 3, h equal to 3. So we can calculate the total number of nodes is 2 to the power 3 minus 1. So this is 7. Okay, so these are two formula where we can reply that what is the minimum number of nodes of height h and what are the maximum number of nodes of height h. So these are some implementation part. So okay. I think we have already tell the what is the in-order traversal, what is the pre-order traversal, and what is the post-order traversal in the last week.
Yes, sir.
Some terminology you should also learn. So terminology is basically what is, so in binary tree or in binary search tree or in AVL tree. So these terms can be important. So this, for example, this is a binary tree. So this first node is called the root node. The node which has 0 child is called the leaf node, also called the external node, also called the terminal nodes. Okay, so you should learn this terminology for the tree structures. So these leaf node is also called leaf node, external node, or terminal node. Okay, remaining nodes are called internal nodes. Okay, these edge is called, these links are called edge or sometimes called the branch. Okay, and siblings. One important term is sibling. So which node have the same parent is called the siblings to each other. So for example, these node, for example, this is A, this is B. So these A and B are the siblings because the parent is common for both nodes. And one another degree terms is used. So degree, what is the degree of this complete binary tree is? What is the basically degree? So if we have a node, this is the, for example, this is a binary tree. So sorry, this is a tree. So what is the degree of this tree? So degree is represent that the how many number of childs are connected to the node. So there are 3 childs connected to the parent node. So the degree of this parent node is 3. If we are asking that the what is the degree of overall tree, so we will choose the highest degree of any node. For example, if we have a binary tree, for example, if we have a binary tree, sorry, if we have a tree like that. Okay, so what is the degree of this complete tree? So what is the maximum degree of any node? So this the degree of this 3, the degree of this node is 4, this is 0, this is 2. So this is the maximum. So the overall degree of this tree is 4. So this degree terms, and one is forest terms. So if our tree are disjoints, for example, if we remove this parent node, so this become a forest tree. So there is one subtree. Second, this is third. Now these all tree are disjoint. So we can say that this is the forest. So subtree, one term is used, subtree. Subtree is a part of the tree. So for example, this is a subtree of the complete tree. This is also a subtree. So these are some important terms. You should know what is the term exactly, what is it represent. So any questions from the AVL tree? If you have any query from AVL. No query. Okay. So next topic is greedy algorithms. So greedy algorithm, basically what is the greedy algorithms? So these are some points given in the lecture slides. So need to make a sequence of choice to achieve a global optimum. So at each step, if we choose the optimum selection to find out the global optimum solution, so that is this approach is called the greedy approach, but it not guarantees that we will get the global optimum solution by this approach. So like you have already seen these algorithm, discussed algorithm, Prim's algorithm, Kruskal algorithm. So at each step we choose the uh, optimum value for the next step. So for example, in Prim's algorithm or Kruskal algorithm, so in Kruskal algorithm we choose the minimum weightage as for each time. Okay, so same for the shortest path algorithm, digest algorithm. So in this case, we always choose the node which have the shortest distance from the source node. So this type of uh, approach, this type of approach is called the greedy algorithm, where we choose the optimum value at each local steps. So at each stage, make the next choice based on the some local criteria. So each time, on each step, we will choose the optimum value on based on the local criteria. So never go back and revise an earlier decision. So we will never go back. So similarly discuss digest algorithm. So when you have already seen the digest algorithm not work for the negative weights. So because if we have selected the node for the next step, so we will never check the previous visited node. If a graph contains the negative weight, so this value becomes changed if we check the previous node value with the negative weights. So in greedy approach, we always select the optimum on each steps, but we will never check the previous step again. So drastically reduce space to search for solutions. So every time problem size is reduced, a greedy strategy needs to prove for optimality. Yeah. So this this approach is required to prove the solution is optimal or not, because sometimes the solution is not optimal for some type of problems. So there is one example which explained in the lecture. So interval scheduling. So interval scheduling. So this is the scenario example where, for example, if IIT Madras has a special video classroom for delivering online lectures, so different teachers want to book a classroom. Slot may overlap, so not all booking can be honored. Choose a subset of booking to maximize the number of teachers who get to use the rooms. So we want to actually perform uh, some bookings. There are many requests for the bookings, but we cannot give the slot for two which have the same times. Okay, so but we want to perform the maximum number of bookings. So what we can, what we strategy we can follow. So for example, yeah, this is the one questions for the activity. So yeah, these are some activity. So A, B, C to H. This is the start time and finish times. Okay. So we want, but so how we can arrange this activity so the maximum number of activity we can perform. So this is basically the purpose of this interval scheduling. So what the solution algorithms is, so how we can solve this problem. So algorithm is, first we will sort all job which waste on end time in increasing order. So we will sort all the jobs at the based on increasing value of this finishing time. Okay, so we will sort the job increasing value of this finishing time. After that, take the interval which has earliest finish time. We will choose the activity which have the earliest finishing time. Repeat next two steps till you process all the jobs. So these are the next two steps. Eliminate all interval which have start time less than selected intervals end time. Okay, so if interval has start time greater than the current interval end times, add it to set current interval to a new interval. So we can perform this. We can solve this easily. Okay, so we have a for example we have a these 8 activity. Okay, A B C D E F G. Oh yeah, 8 activity. So we will first we will sort these activity by the this finishing time in increasing order. So what is the smallest value is finishing is A. Okay, so first is A. So what is the start time is 1, this end time is 2. Second value is now 4. So B, start time is 3 and end time is 4. What is the next? B, start time is 1 and end time is 4. So now next increasing value is this 5 here. So E, 4 and 5. Yeah, so next value is 6. So this is C, 0 and 6. After that 9, 10, 11. Okay, so 9 is F. This is 5. This is 9. Now H. So this is 8. This is 10. Now G, 9 and 11. So we have all. So now we have sort the all jobs according to the finishing time increasing order. So after that we will pick the jobs for perform. We will pick the first activity we will perform. So what is the earliest time is finishing time is 2. We will pick this activity to perform. So this will be selected. So what is the end time is 2. Now we will compare this end time to the next activity start time. Okay, if start time of the next activity is greater than the this end time of this activity, so we will pick for those activity again. So now the start time of this B is greater than the end time of this A. So we will pick. So now next activity is B. We can perform. So it is also select. Now end time is B is 4. So we will check the next activity start time. So this is 1. This is less than the 4. So we will not pick this. We cannot pick. Same for the next activity. Yes. So this is the 4 and E activity is start at the 4. So what is the condition is given? So if any activity start at time 0 and finish at time 4, then other activity cannot start before 4. It can be start at 4 or after. Okay, so we can start this activity now. Okay, so ending time and finishing time is equal. So we can choose this activity also. So now this is the next activity E. Now end time is 5. We will compare the start time with this 5 value. So now next is C. So 0 is less than this 5. We will not pick. Now next is 5. So 5 is equal to this 5. Okay, we can select this now. So this is F. Okay, now end time is 9. Okay, so now H start time is 8, which is less than 9. So we cannot pick this. And now next is G. So 9. So 9 is equal to this 9. So we can select this one. So now this is G. So these the total number of maximum activity we can perform is A, B, E, 5, G, F, G. So total number of 5. This is the solution. So we can. So this is the greedy approach to find the solution for this type of problem, interval certitude. Okay. So we can. So using this algorithm, we can write the solution code for. This is the easy. Right? Second, next topic is minimize lateness. So actually, what is the scenarios for this minimize lateness is, for example, if we have a IIT Madras has a single 3D printer, a number of users need to use this printer. Okay, so each user will get access to the printer, but may not finish before deadline. Okay, so there is one terms is here. This is the deadline. Okay. Goal is to minimize the lateness. So our goal is to minimize the total deadline value. total this lateness value. So what are the scenario? For example, these are some job. Okay, I'm just taking the example. So these are some jobs. So here first value is the activity value. So 1, 3, 6, 2, 2, 9, 3, 1, 8, 4, 4, 9, 5, 3, 14, 6, 2, 15. Okay, so this is the activity ID, basically ID. This is the total time duration of the jobs. So we can see the duration, and this is the deadline. Okay, so how we can perform these, how we can schedule these activity. So where the minimum total lateness, so total lateness is minimum for the scheduling. So what is the lateness is, for example, if we are performing, so the deadline for this ID1 is 6. So for example, if this activity performed after this 6 value, so for example, this is finished at the 7, so the lateness value will be 7 minus 6 is a 1. Okay, so if any activity performed after the deadline, so this is the value, is the lateness value. So how can we reduce this total lateness of by our scheduling? So same things, we will sort all these activity according to the deadline value. So this is the algorithm. Sort all the jobs in ascending order of the deadline. Start with time 0, T0, and for each job in the list. So this is the steps you can perform. So first step is we will sort these activity according to the deadline value. So what is the minimum value is now this 6. Okay, so 1, 3, 6 is the first value. After that, this is the 3, 1, 8. Yeah, second value. Next is 2 to 9. Third is 4, 4, 9, and 5, 3, 14, and 6 to 50. So this is the sorted. Okay, so after sorting, we will start from the 0, and this is the time for execution. So we will pick the first activity, and first activity will start. So we are marking that we will start from the 0 value. Okay, so this is the 3 time. So this will be finished at the 3. So the lateness, what is the lateness for activity 1 is, because deadline is 6, but we are completing this activity before the 6, so lateness will be 0 for that. Okay, so after that, this is the first activity. Okay, I'm marking that 1. So we will pick the next activity. Next activity is 3. Okay, so what will be the time for this is 1. So 3 plus 1. Okay, so what is the total value is 3 plus 1 is 4. So this 3 activities completed at the 4 time. Total at the time 4. So what is the deadline is 8. So it is also completed before the deadline. So the lateness is 0. So now next activity is 2. Okay, so what is the execution time is 2. So now total time is from 0 is 3 plus 1 plus 2. So this is 6. Now this completed at 6. The deadline is 9. So it is also performed
Sir,
before the.
I have a question.
Yeah.
Sir, so when we are sorting by deadline, are we also giving a second key of duration that in the third and fourth case where deadline are equal, we must get the one with the smaller duration to come first?
So okay, so sorting. 1 second, I got this. Sort all job in ascending order of the deadlines. Start with the time t equal to 0 for each of. So it is so algorithm says that we have to sort only according to the deadline value.
Will
according
it
to
not
the
be
deadline,
useful
no,
to?
yeah, it can be swap. I think so. This 4 activity come before this second activity. So this is the not part of the algorithm. So we will just sort the activity according to the deadline, not to the execution time.
Okay, will the duration make a difference in lateness? I think it might.
I think it not. Okay, so we will take both case. Okay.
Okay.
So now total is 6 and deadline is 9. So it is also lateness is 0. Okay. So now we will choose the fourth activity here. So what is the time is 4. So this is 4. Now 6 plus 4 is 10. Okay, so total the time completion time is 10 and deadline is 9. So now lateness is 1. Okay, for this one. Now we will pick 5. So it takes 3 times. Now 10 plus 3 is 13 and the deadline of this is 14. Okay, so again lateness is 0. Now we will pick the 6 and um, 2. Okay, 2. So 13 plus 2 is 15. So this is finished at this time. So 15. Okay, so we are also completed at the 15. So deadline is 15. So this is also 0. So total lateness is complete. We will sum this value. So this is 1. Okay, so this is the solution way to minimize the lateness. Okay, so for example, if we swap these value, so it makes any change or not?
Like if it was 12 instead of 2 in the third case, then both would have gotten late without second sorting.
Okay, just I'm just calculating this one. So this is 3, this is 3, 1. Now this is 4. Okay, so 3 plus 4, 4 plus 4, 8. So this is 4. 4 plus 4, 8, and deadline is 9. So now it is 0. It is 0. Now it is also 0. Okay. So now we will select 2. This is 2. I think it will not affect because lateness is
Sir,
decrease
in
here.
this case, it won't affect, but I was saying if in the third case, instead of 2, it was 12, both parties would end up getting late without second sorting.
So what you want, what you actually changing the value? So in second?
No, in the third instance.
Okay.
So instead of 2, if the duration was 12.
12.
Yeah.
Okay.
Now the ordering matters.
I don't think it should matter because when you're calculating minimized lateness, you're taking a cumulative effect of the jobs. So irrespective of the order in which you perform, if the what was this third deadline is crossing, it would cross in any case. So the cumulative effect of any order would be dependent on the deadline rather than the duration any job is taking. That's my understanding.
Yeah, so I think minimum lateness will remain the same. So for example, if you're taking this order, so okay, just consider that once again. So what will be the, okay, I'm just removing this part. Okay, so for example, if we are taking the same process, so this is the one, this is the one. So next is, this is 3, next is 3, 1. Now we are taking 2, 2. This is taking 12. Okay, so after that, this is 0, this is 0. Now, so 4 plus 12 is 16. So deadline is 9. So this is 7. Okay. So we will choose next. This is 4. 4. So 16 plus 4, 20, or no, this is 9. So the total lateness is 11. Okay. Now 4, after that we will pick 5. So now 20 plus 3, 23. So 23, This is called the 9. Okay, now 2. So 25, this is 10. So minimum lateness will be 7, 11. So this is 20, 30, 37. Okay. If we swap the value, for example, if we consider this above one, so what will be the lateness? So if we are considering this 1, 3, then 4. So this is 0, this is 0. If we are taking this 4, so now this 4 step. So 3, oh sorry, yeah. What I missed? Oh, correct. This is 1, 4. This is 4. So 4 plus 4, 8. So now it become a 0. Okay. Now we will choose the 2. So this is 12. So 4 plus 4, 8 plus 12, 20. So 20 minus 9 is 11. So now it become 11. Oh, it's changing. So okay, so the 2 now 5. 3, 1, 4, 12. So now 3. So 20, 23, 23 is minus 14 is 9. Same for the 6. So 25. I think it is reducing. 11, 10, 21, 30. Yeah. Yeah. So value is changing. So because of that, we said no. So we have to prove this, because the local greedy algorithm is not always the global optimum. So there is a need to check the our solution is the optimum or not. The one situation. So every greedy solution requires the proof for the correctness. So I think it's not of or we skip any part. Okay, just I'm looking the lecture. One second. What is the slide actually? One second. 7. So we can minimize lateness. Minimize lateness. Yes, this is the lecture slides. Make a sequence local strategy. It's the strategy, greedy strategy. Schedule request in increasing order of the length. Counter example. So this is the strategy 3, schedule request increasing order of deadline. So no invoice deadline, only difference can give the order of requests with same deadline. Yeah, this point is difference can be the order of the request with the same deadlines. Because reordering jobs with the same deadline produce same deadlines. This point is given, but reordering jobs with same deadline produce same lateness.
Yes, sir. The same things are explained in the proof also.
So how our solution is different now?
Sir, maybe because in the solution, the case you were taking, the deadline is more than the time required. Try changing that.
So what we are taking actually 212. Oh, yeah, this is the incorrect actually.
But if we do take an 8 or 7, even then the problem will remain.
I think no. Because here we are taking the execution time is more than the deadline. So this is the case. Okay, just I'm taking one more example which you are saying. So for example, if we have a 1, 3, 6, 2, 9, 3, 1, 8, 4, 4, 9, 5, 3, 14, 6, 2, 15. So what value you are you want to change? So after sorting, actually, so what will be the 1, 3?
So we could take 8 maybe.
Okay, I'm just sorting 3, 1, 8, 2, 2, 9, 4, 4, 9, 5, 3, 14, 6, 2, 15. Okay, so what value you want to change now? So
8, that will be 1 less than 9.
this
Yes,
okay,
yes, sir.
8. Okay, so if we are choosing the, for example, this first activity, then this is 3, then third activity, this is 1, then 2 activity, this is 8, and 4 activity, this is 4, this is 3, 6, 2. So lateness is 3, 0, and 4, 0, then 4 plus 8, 12. So 12, this is 3. Now 12 plus 4, 16, 7. Now 16, 16 plus 3, 19, minus 5, and 21. 21, this is 6. Okay, the total is 10, 21. So after that swapping, so 1, 3, and 4. Now 4, so this is 4, this is 8, 3. So after, so this is value is 0, 3 plus 1, this is also 0, plus 4 plus 4 is 8, this is also 0, 8 plus 8, 16, this is 7. So 63, 19, and 5, and 2, 26. The value is changing. Okay, so I think this is not the same deadline, we do same lateness. Okay, I think this is, I have to confirm these things to the sir, then I will reply on that. Because this is not satisfying actually. Version has an version of I appears before J, but okay, so I will confirm this things to the sir. Then after we will revert on.
Okay, sir. Thank you.
Okay. So this is the basically algorithm for the minimized lateness. I think this is one counter example. So after that, next topic is, so there are many messages in the chat box.
Sir, in the proof, sir explained that if we swap any two tasks, then that will only that will not increase the lateness. That will only that it can decrease the lateness, but that will never increase the lateness. So that is the proof.
But this one line is reordering jobs with same deadline produce same lateness. This is not looking correct, no?
Yeah.
Okay, I have to check with sir. Yeah. If you are reducing things is given on the slide, so I think it is correct. But here mention is same lateness. Okay, we will check.
What?
This. Yeah.
Oh, there's a claim that saying that there were no inversions and no idle time. Are we in the question that we changed? Are we have we
What is the
confused
wrong?
with that assumption?
So what is the wrong in this person actually? Something is wrong. So if this 2 is, for example, 2, 8.
So it's saying only if there are no inversions or idle time, but in that case only it's the scenario where it won't have any effect on the lateness.
So what do you mean by inversion here?
That's what I actually wanted to understand in this slide.
But I think earlier the duration was summing up to the maximum deadline. So earlier the sum of durations was 15. I think maybe that has something to do with it.
Sorry, I'm not getting what you're trying to say.
Before
Earlier?
we changed the 2 to 8, the sum of durations was 15, I guess. Maybe that has something to do with.
I think it is not.
Sir, inversion is basically like when I appears before J and deadline of I is greater than deadline of J. So that situation scenario is called inversion.
Okay. So.
But that didn't happen, no? Deadline of I and J were same, so this won't be inversion, no?
Yeah, this is not inversion, but I'm explaining it to.
Yes, yes. Thanks.
Okay. So okay, I'm also confused for this situation. So I will clear. I will apply your clear all. Yes.
So here the start time plus duration is greater than the deadline.
So where is the start time here? Start time is
The
not.
2.
2 is the idea of activity.
Sir,
Okay, sir.
what does that mean? Like idle time? Is it like lateness will be 0 in the idle time?
Lateness is 0. No, idle time mean what?
Yes, sir. I'm asking you, like, what does it mean by idle time?
So idle time is nothing. Actually, lateness is representing that if lateness is 0, that means our process is performed before the deadline, before or same at the time of deadline. So lateness represent the value if our process is completing after the deadline. If it is completing before the deadline, so we will take the 0 lateness.
I guess, sir, something like that, like if the lateness of complete scheduling task is 0, then that is called idle time. And in that case, the if we reorder the things, the deadline will, like, lateness will be same.
This thing.
I'm not sure about it. Sir, if you can confirm like what is idle time, then we can say.
Yeah, so ideal time is regarding the minimized lateness. I did not see where is the ideal time term used.
So here we have the conditions. Any two schedules with no inversion and no idle time have same maximum lateness. Same word is also here. So we know the inversion thing, but we don't know about idle time, what exactly this is.
Okay, any two schedules with no inversion and no ideal time have same maximum. Okay. Also, idle time. Only difference can be order of request is single. So okay, I'm also not clear about this. I reply on that to clear all these things. I have to discuss with the sir. Okay, so I think in next Saturday live session I will clear on that live coding session.
Okay, sir.
Okay, so next is Wookman algorithm. So the purpose is basically for Wookman algorithm is to generate the Wookman codes, and this Wookman code is basically used to perform the data compression. So, for example, if you want to send a message to on our internet, so if size is large, so we apply some compression method like a zip. We create the zip folder for any large folder, so it reduces the size of the complete folder. So basically, we use this main coding for the data compression purpose. So how we can generate the Wookman code using Wookman algorithm? So this is the algorithm basically. So initially we have the frequency of each character. So for example, if we have a strings or if we have a message, so initially we calculate the frequency of each character. After that, we create a Wookman tree using this frequency, and using this Wookman tree, we can create a Wookman codes. So how we can create the Wookman tree and how we can generate the Wookman codes. So for example, if we have some character A, B, C, D, E, okay, take one F. We have given a one frequency 40, 10, so 5, 15, 25, and 30. Okay, so these are the frequency of each character in the message. So we can create the main codes for each characters using this frequency. So what is the algorithm is? Algorithm is basically we always pick the two minimum frequency characters or minimum frequency value and create the Wookman tree in the bottom up manner. So we will choose the two minimum value. So initially we have these 40, 10, 5, 15, 25, 30. Okay, so we will start from the bottom. So for example, we will just select these two. Okay, so 10 or 5. So we can manage in any order. So we can make a 10 is on the right side or 5 on the left side, or we can change that. So for example, if we are taking small value on the left side and large value on the right side, sorry, small value on the left side and right value on the left side. So we will create these things. So these are the main frequency of the character. So we mark that this is the character frequency. So we represent that this is like an external node, square box. So this 5 representing to the C and 10 representing to the B. Okay. So after when we create the summation node, so we will create a one parent node for these external nodes. So we will put the value of the sum of these nodes. So 5 plus 10 is 25. So we will put that here. So basically every time we will remove these two minimum frequency from the sequence and insert the sum of these frequency. So now we have a sequence 40, 25, 15, 25 and 30. So we can also mark that this is the character frequency, okay, and this is the summation value we have already used in our tree. So we will pick the next two smaller value. So we can pick this 15 with any one of the 25. Okay, so we can pick, for example, if we are selecting this 25, so we will mark this 15 as a external node with this internal node 25 value. So this is the 15. This is the character of this D. Okay. So next upper level parent will be 25 plus 14 is 40. Okay. So we have already select this one. So now this is the 40. This is the external, and this the calculating value is 40. This is internal node value, and this is 25. Yeah.
Sorry to interrupt. Isn't the sum of 5 and 10 would be 50? Or am I missing something?
Oh, sorry. Yeah, 15. I missed. Okay, so now two smaller values. 15, 15, 30. So this is now 30. So 15 plus 15 is 30. Okay. Thanks for pointing out. 30. Yeah. So now this is the internal node and remaining are the external nodes. So we will pick next two nodes. So this is 25, then this is 30. We can select any one of them. So 15, 15, okay. So 10, 5, yeah, this is correct. So we will select once again. This is the, so we can take here. We are taking a small value on the left. So 25. So once again, we will create a parent node. So this is 55. Okay. So now we have a value 40. This is external remaining. 30 is also external remaining. And now here is value is 55. Okay. So we will pick the next two smaller value. This is now 40 and 30. Both are the external. So we will create this external separately. So this is called the 30. This is 40. So this is 30 for the F and 40 for the A. Once again, now this is 70. Okay. So now 70 and 55. Both are internal. So we will connect both. So 125. Okay. So now this is the augment tree. After creating this augment tree, we will mark that the left as 0 and right as 1, 0, 1, 0, 1, 0, 1, and 0, 1. Okay. So now we can find out the code for each character now using this tree. So 25 value is for E. Okay. So what is the code for A now? So A is here. Now we can traverse from the root. Code is 1, 1. Now what is the code for the B? code is B is 0 1 0 1. So 0 1 0 1. C, so code is 0 1 0 0 0 1 0 0. D, so code is D for 0 1 1 0 1 1, and E for 25, so 0 0. Okay, and last F, so F is 1 0. So these are the Wookman codes. There is one property inside these codes is these codes are called prefix code. Okay, so what is the meaning of prefix code is here. So prefix code is basically so there is no code here which comes on the as a prefix on the other codes. So if you are checking these codes, so you can find out that there is no codes is available here which is the part of the as a prefix for other code. So if you check this 1 1, this cannot be part of the prefix of the another code. So there is you cannot find that 1 1 is not a part of any prefix of others. Same for the 1 0, there is no 1 0 at the initial part of any other codes. Now 0 0 0 0 is also not a prefix code for others. So this type of condition is called that these are the prefix code. So Wookman tree is always produce the prefix codes for the characters. So there are many questions can be generate using this Wookman codes. So for sometimes this question is also asked. So sometimes codes are given for the each character and find out these codes are valid or not. Okay, so for example, if I'm just writing that A, B, C, D, E, F, I'm just writing that 0 0 1 1 0 1 1 1 0 0 0 1 1 0 and 0 1 0 0 0. Okay, so can anybody tell me these are the valid codes for these 6 characters or not?
No, sir. I guess 1 0 is in B also prefix.
Yeah. So you can easily verify this by just checking that this is prefix code or not. So this one is the part of this B also as a prefix. So this code cannot be generated by any Wookman tree. This situation. So these are not the valid code, Wookman codes. Or sometimes code are given and find out that what is the actual message. So for example, code is given 1 1 0 0 1 0 1 0 1 1. So what is the message for that? If tree is given, what is the message for that? Okay, so for example, you have a code, you can identify by this. What happened if tree is given, not the code is given, so only tree is given, and you have a parent node, you have a reference of the parent node, and one message is given. This is the code, and asking that what is the value of the actual message. So how you can find out these messages using this given code? So if you yeah.
So sir, we can simply traverse left or right depending upon the value of 1 or 0.
Yeah, okay, correct. So you can traverse the tree according to these given values. So when 1 is appears, so you move to the right side. When 0 is appears, so you move to the left side. When you reached at the leaf node, you can mark that this is the character. After that, you have to reverse back on the route. So for example, for this example, so first character is 1. Okay, so in tree, you will move to the right side, this one, okay, on the route. So next character is also 1. So then you once again, you will mark on the right side. So after moving this one, you have reached or at the leaf nodes. So you have marked that the A is appeared. So when you have reached at the leaf node, you come back on the root node again. So okay, so once again 0 you will start from the root node again. So this is the 0, next 0. So now E is come. You can mark that. Next character is E. Same for next 1 0. So you will start from again root node. So 1 and 0. Now 30 you have already reached at the leaf node. So you can mark that this is F. Once again. So now 0 1 1. So, okay, so you start from the 0. So what is the 0 is this 0. Now 1, now 1. So you have reached at the D. So you can mark this the D. So actual message is AEFT. So you can traverse the tree and you can find out the message, actual message using the code. Okay. So these are Huffman codes. Yeah, these are the implementation. Okay. At each recursive step, extract letter with minimum frequency and replace by composite letter with combined. So these are some steps given in there. So using binomial heap or minimum min heap, you can reduce the complexity to big O K log K for the Huffman code. So you have already learned the max heap, min heap. So where you have, if you create the min heap of size K, so where here K is the number of characters, so you can create the min heap, and after that every time you remove the min element, two min element, and then you can create the Huffman tree. So using binomial heap, the complexity of this Huffman code is Huffman algorithm is K log K. So these are some topics in week 7. So if there is any query on any topics of week 7 or a previous one, you can ask.
Sir, I was unable to code that Huffman coding recursively.
Yeah, so this is the implementation given here. So you want to create the Huffman tree from the bottom up manner, no?
Yeah.
Yeah, so this is the way. So actually here what we are doing, so for node, we are creating a nodes. So we have to see in the starting. So main code is empty, carry list as frequency. This is the process to create the frequency. Okay. Unique care frequency list not append. I think one question is given in the practice assignment, no? For based on that Huffman tree.
Yes, sir. I did this question using this like iterative method like you used, but I am like sir explained in the lecture, we can do it recursively. So how?
So this is also recursive actually. So
No, sir.
not recursive.
No, sir.
Huffman. Okay.
Since we are creating all the nodes in the second for loop and then attaching connecting all those.
Yeah. So we are every time we are selecting the minimum frequency nodes and appending into the same list.
That's the method as I use, but I want to know the recursive method. Like how can we implement that? If you can give some hints.
So recursive, I also did not try to create a Huffman tree. So recursive. Okay. Code, you have to see, you have to implement this code. Okay, so I have to think about that, about how we can generate the recursive solution for this tree. Okay.
Okay, sir.
Yeah. Okay. So after implementing this, I will add this recursive solution in this summary notes.
Okay, sir.
So any other query from the previous weeks also? There is no query.
Sir, can you discuss week 6 GRPA 2 and 3?
GRPA 2 and 3. Okay, so I'm seeing that. What is the GRPA 2? Week 6. So max less than root. So solution is available. So max less than root. What is the key question? I have to see. Write a Python function max less than root that accepts a root node of the binary search tree and a number k and return the maximum number less than or equal to k in the tree. If k is the less, okay. If k is less than every number in the tree, return null. Okay. So first of all, we have to find out the node which has the value k. So what is the solution? So this is the max less than. First is the max equal to root value. We are starting from the, so we are considering that the root value is the max, and we will traverse these tree. Okay, so while not dot temp is empty. Okay. Template. So elif temp dot value in okay. Let's count if k is greater than equal to max, return max. So what is the logic to log in? So max length.
We are traversing the tree and checking if there is some value which is less than k, and we are calculating the maximum of those values which are less than k in the tree.
So where we are storing the maximum value?
In the maximum variable in the elif condition, sir. So if in the first if condition, if the value is greater than k, so we are just moving left side because we don't want to store the value which is greater than k. But in the elif condition, if value is less than equals to k, then we are storing that into maximum variable, and moving towards right, because we need like bigger value than the current value.
Mhm. Okay, so if temp dot value and okay, let's see temp. Okay, if I'm creating the key, for example, if we have a tree, so 15, 10, 5, 7, 12. So if we, for example, this is a binary search tree, and if I am finding that
K is 13.
k equal to 13, okay.
Yes, sir.
So what is the maximum value which is less than? So what should be the answer is so 13. So we will 13
Answer will
answer,
be in this case, sir, 12.
12. Okay. So what are the elements is less than 13 or equal to 13? Is 12, 10, and 5. Okay. So what is the maximum in this is 12. Okay.
So from starting from the root node 15,
Yeah, we
first
will
we'll
start
compare
from
15 with 13. So 15 is greater than 13, so we'll like
we
move
will
left.
move to the left side. Okay, okay. Yeah. So yeah, what we are doing actually, we are comparing to the root node. If value is the max greater than 13, then we will move to the left side. Then we will compare again. Now value is the less than 13, then we will move to the right side. Okay. Now again 13 is greater than, then again move to the right side. Now this is the less. So 13 is now less. So okay, so 13 is less. Now there is no element empty. So stop. So we are always storing the max value.
Yes, sir.
Yeah, this is the temp value. Okay. Okay, so initially the max value is 15. Once again, we have moved to the now max
Sir,
value is
initially the max value is nothing because 15 is greater than 13, so we cannot assign that to 15.
no. So initially in code solution code,
It's assigned to the root value.
yeah, max is equal to root dot value.
Sorry, sir.
Yeah. So initially max value equal to root value. So max equal to 15. So if we are moving to the left side, okay. So what we are changing in the code actually, if temp dot value is k is less than the temp, okay, we are moving to the left, not storing the value. Okay, but the when value is greater than temp, so we are storing the.
But sir, if k is equal to temp value, then you don't want to move to the right, right?
So let's return on. So if k is greater than equal to max.
No, in the elif statement, if k is equal to temp dot value, then
Mhm.
you want to move to the left and not to the right.
Yeah, the equal to condition should be in the first part, if condition.
Yeah.
Yeah, you're right.
No, so if k is greater than equal to max. So for example, if we are taking the k equal to for example 15, okay.
Yes, yes.
Okay, if k equal to 15, so what will be the answer actually? So
We have to move to the left
according to
side.
the k equal to, so max value is the 15 now. So we will check temp dot value and k is less than temp. So this condition is not satisfied. Okay, we will move to the right conditions. So if temp dot value and k is greater than equal to temp dot value. So yes, this condition is true.
So, sir, this is wrong actually because we should move in on the left side. So the equal to part should be in the if condition.
And if k is greater than,
Or we should just simply, because we have to check the value which is small, like less than k. and which is maximum.
So temp. K is greater than equal to if K is greater than equal to max, return max. Else return none. So what we are moving to the right. Max equal to temp dot value. So answer is affecting using this method or not? So is there any issue using this method in test case?
I don't think you can test this on the platform anymore, right?
So the problem with this code is like whenever we have the value, like whenever we will have a single node, let's say only 15 we have the node, then we'll assign that to maximum will be 15 only, right?
Yeah, 15.
And what if our K is also 15? Then the answer will be 15, but we have to return none in that case, because if the value is same, then we have to return none.
No, so in last condition is that K is greater than equal to max. So why it will return none? Because for example, if we have a single node,
Yeah.
okay.
Yes,
So if temp dot value and so temp dot value is basically 15. Value is okay, and K is greater than equal to, this is also satisfying. Okay, so max equal to temp dot value. So temp is root basically. So the value is max inside is remain the 15. So there is no node after that. Is temp equal to temp dot right.
Yes, sir. Okay, sir. We have to calculate maximum less than equals to. That was the thing I was missing.
Actually, we are moving to the right part after assigning the value of node inside the max. So max will remain the 15. After that, this value will be right. So value of 15 will return.
Yes, sir. It's right.
Okay, so is anything wrong, for example? So what happened in this case? So we are starting from the 15. So max value now is 15. Then we will move to the right part. So next, now temp equal to temp dot right.
Sir, it will create issue when we take the when we have to calculate max less than, strictly less than equals to K, strictly less than K, not equals to.
No, is it correct or not according to you now?
It is correct now, sir. For the given condition, it is correct.
Okay. Oh, I am actually confusing this. If value is equal to this temp dot value, for example.
Yes, sir.
So we are moving to the right. Okay.
Yes, sir.
So for example, K equal to 15, and we are comparing this K. So this is not less than, this is equal to. So we will moving to this now temp come here. Then we will compare again temp dot value is 20 and value now condition is K is greater than. Okay.
Sir, here you can simply create a different elif condition when K equals to temp dot
Okay,
value.
okay, now okay, got it. So now when we move to this node, so the K is not greater than this 20. So the stop, we will stop the process. Now max equal to 20, 15.
Yes.
I didn't get it, sir. What if K
Mhm.
equal to 15?
So actually we are finding out the what is the maximum value which is less than the 15 value actually. So for example, so okay, this is the 15 is given. Okay,
See,
for example, k value is 16. Okay. So what are the less value available in the tree which are less than 16? Can you tell me? So the value which are less than 16 is 5, 10, 12, 14, and 15. Okay,
15,
correct?
yes.
So what are the maximum value from these? So the maximum
15.
value is 15. So answer should be written is 15.
sir, we have to consider less than equals to. So 16 will be answer.
No, but oh, 16 is also there. Okay. So actually, I taken this value. I'm considered that 16 is not available. So if 16 is available, then 16 is also covered inside. Now answer is 16. So condition is given if k is present, then we will return the k value as an answer. Okay. For
But
example,
the
yeah.
code is not like a good code, because we are like, after checking, like let us consider a case 15 is the node and k is also 15. So in that case,
Yeah, we can improve this. We can directly improve this if temp dot root equal to value. If value equal to k, so we can directly return.
Yeah.
Yeah, okay.
Yes, sir.
But still we are moving. We are checking the another condition.
We are moving on the whole right part and checking.
Yeah, it's
Yes.
okay. Yeah, we can improve this part of the solution codes. So otherwise, so question is simple. We are just compare the element value. So for example, now this is k equal to 17. Okay, so we will find out that the 17 we consider that max value is 15 initially. So what is the condition? We will check that the k is greater than or less than 15. So k is greater than, we will move to the right part. Okay. Now we will check here. Now k is smaller than of this 20. We will move to the left part. Okay. Now here k is greater than, but we will move to the right part, but there is no node on the right part. So we will return this 16 as an answer. When we are moving to the right part anytime, so we will first store the we are changing this max value. So initially max equal to 15. When we are moving to the right side, so now max equal to 20. Now when we move to the left part, okay, so we are not storing this max, so max remain the 20. So after that, when we are moving to this right part, so we are storing that max equal to 16. Okay, so this is the condition where we are find out that there is no node available, so we will return the max after that according to the code. So initially max equal to root node, at temp equal to root. So while not temp is empty, temp dot is empty. Okay, if temp dot value and k is less than temp dot value. So when this condition is true, when k is less than temp dot value, we are just moving to the left, not changing the max value. But when the value is equal or greater than, so when the value of k is greater than or equal to temp dot value, so first we will store the value inside the max of the node, then move to the right part. Okay, here we are changing the value according. So according to this, we can find out the maximum value which is less than the k, less than or equal to the k. Okay, got it? What we are doing in the solution?
Yes, sir.
Okay. And 3, what is the 3? Min max. Given an array based on min heap, write a Python function min max array to convert array to max heap. The function should change the original array to max heap. The accepted time is complexity 0. So this is one, I think, min heap is given, and you have to convert this heap is max heap. So you can simply apply the process heapify process on the node. For example, what you should do, how we can solve this. So for example, if we have a min heap, okay, so what is the type of, for example, this is 1, 2, 3, this is 4, this is 6, this is 5, this is 8. This is a min heap. We want to convert this min heap to max heap. So we will apply the heapify process from this node. Okay, so similarly, we used this method to create the max heap process. Okay, we can apply the max heapify process from this parent node, last parent node. So first parent node is this, second parent node this, and third parent node is this. So after that, all are the leaf nodes. So we will apply the max heapify process. We will compare these three elements and find out the maximum value. So after heapify this process, so what is the maximum value is this 8 in all three. We will swap this the parent node. So after this process, so now it become like 1, 2, 4, and 8, 6, now 5, now 3. Okay, now we will apply the max heapify process the next this 2 node. Okay, so what is the maximum node on these three? 6. So we will swap these 6 to 2. So after that, we will get the this 1, 6, this 8, 5, 3, this 4, and this 2. Okay, now we will apply the max heapify process on that node. So what is the maximum value on these three nodes is 8. Okay, so after that, 8, 6, 1, 4, 2, 5, then 3. Now after swapping this, so we will check the child node again. Okay, so the condition is the heap is properly max heap or not. So we will check once again this node. So we will apply the max heapify process on this node. So what is the maximum of now? This is 5. So this is 8. This is 6. This is 4. This is 2. This is now 5. This is 1, and this is 3. So this is now max heap. So basically, we are performing the max heapify process. So solution code is also, I think, similar to this one. Yeah, heapify process.
Sir, in this one, my question is, what if there is not a right leaf? Because sometimes it might happen that you only have the left kid.
So for what type of situation you are saying that?
So if I have,
for example, this is the 1, 2, 3, 4.
If you have even number of nodes, say 10 nodes.
Okay, so I'm taking this is the condition 5, this is 6, this is for example 7. Okay.
Yes.
Okay. So actually, what is the formula to start the heapify process? From which node we are start from actually? So
and
this
is the division 2 minus 1.
len of heap. So what is the len of total heap is 8. So for example, I am writing the heap minus 1. Sorry.
Yeah.
2. Then minus 1. So total, what is the length of this heap is 8. 8 divided by 2 minus 1. So this is 4 minus 1, 3. So we will apply the heapify process from 3 node, 3 to 1, 3 to 0, sorry, 3 to 0. So what is the index is actually 0, 1, 2, 3, 4, 5, 6, 7. So this is the node where from we will start the heapify process. So in this process, if there is no node, so we have to maintain one condition. If when we calculate the child value, okay, so how we can calculate the child value is So we are, for example, we are creating the left child index is so 2 into I plus 1. What is the formula is for R? 2 into I plus 2. So what is the I value is 3. So 3, this is 7. Now this is 8. Okay. So we have already considered this condition for the right node. If the right node index is greater than the this right index should be less than the size of the heap. So what is the total size of this? 8. So value should be less than to the this heap size. If not, so we will not consider this right child. So I think this condition is given in the code. Yeah, so this is one. No? So we are considering this condition. If R is less than equal to n, so what is the n here? N is the size of the heap.
Okay. Thank you.
So we have to include this condition in our code. Okay. Any other query? So B7, so there is no query. Is there any question or close?
Sir, one more question.
Yeah, Bras.
Like if we have any other problem than lateness, like minimizing the lateness or interview scheduling, and we want to solve that problem with greedy approach. So how can we prove the correctness of that algorithm?
So these interval scheduling algorithm, actually, I think this is the already proved, which sir explained in the lecture.
Yes,
I think
sir.
sir is also explained the proof.
I am asking, like, if I am trying to solve any other problem than these two situations we have, then how can we prove the correctness of algorithm?
So I think there is no standard way to prove, but sometimes we have to. For example, there is one problem. So I'm just discussing with you the coin problem. Okay. For example, we have a coin. So we have different types of coin. So one is 25 coin, coin 20, 15, 10, and 5 and 1. Okay. So we have a different type of coins, and we have a one amount. Okay. So we, for example, we have a one amount 60, and we want to get this amount with the minimum number of coins. So how you can solve this approach using greedy algorithms, and is it correct or not?
Amount coin.
Okay, so you will just take the maximum number of value of the coin, and you can take the any number of maximum coins for any value. So for example, this is the 25. So you can take the 2 coins for the 25. So 2 into 25, and what is the total value is now 50. Then 20 we cannot take, now 15 we cannot take, not 10. Okay, so 1 is for 10. So total number of coin is 3. Okay, so according to this, so this is approach is correctly working or not?
Yes, sir, this is working.
This is efficient. But what happens? So actually, this type of situation we can prove by some counter example. So counter example, for example, if we have a amount 40. So according to algorithm, what solution will not 40. Just wait. 20, 25. Okay, so I'm removing this 15 now. Okay.
Yeah.
Okay, so the answer is correct for this one. Now I am taking this 40 now. So what the solution according to you? So you will take the 1 into 25.
Yeah.
Okay.
10. Yeah.
Now 25 we cannot take. So now 1 into 10.
And 1 into 5.
2 into 1 into 5. Okay.
Yeah.
according to this one. So there are 3 coins required, but we can take this using 20 into 2.
Yes, sir.
Okay.
So there is a contradiction in that.
Yeah, this is the contradiction for this type of problem. So we can simply prove some counter example or some.
And if the algorithm is satisfying all the possible
Yeah,
examples.
so all the possible conditions, if it is satisfying, so that means it is working correctly. So that means this greedy approach is not working in all cases for this example.
But sir, in real life, we can miss those cases.
Yeah. So this type of some proof are required.
Okay, sir. Thank you.
Okay. Any other query? Okay. There is no query, then shall I close? Okay, bye everyone. Thank you.
Bye, sir. Thank you.